question number 6 of the PhilNITS FE afternoon portion of the exam. In this question, we are supposed to answer something about the big O notation. And remember that our algorithm is a counting sort algorithm. And remember too that an algorithm is supposed to be a set of instructions. That's why in this case we have 3 steps, and from there we'll be able to also identify the correct big O notation for this question. Now when I was answering this, I was focusing more on the actual computer code, and from here we can see that the first part is pretty much just assigning default values to the variables, to the containers. And when we say containers, it includes the arrays, which are containers of containers. Later on, we have steps 1, 2, 3 here, which we need to execute in sequence. And if we go to the sample code for step 1, it's saying that there's a for loop here, and we have to start from 0 and count until 9. And then for each of the count, we have to do something inside it. And I think when I was answering this, I didn't worry too much about what was inside, because we can see that it's well, simply assigning a value to the variable. And what is even more important to help us understand what would be the correct answer is this part where you got the for loop. If we look at step 2, we again see here a for loop, and inside we have another set of instructions. And even though we have a conditional statement here where if the value is greater than 0, that's when we do this part here. I think really the for loop would help us figure out the correct answer again in this case, and later on we'll explain that a little bit more. Step 3 also has a for loop, and inside it we got the values being assigned to another container, and so on and so forth. Now if we look at the choices, we have here a set of choices where you have the big O, and when I was answering this, I was able to find the correct answer, which is O of n, pretty much because of the for loop, where when we're talking about the for loop, it means that if we're starting at 0, then we're counting until the maximum number, which we can say is n. Then in that way, that's how fast the computer program will run during execution. It's runtime execution. So if it's gonna count from 0 to n, then we know that that's gonna be how fast it would be. But again, if we look at the other choices, we want to know what they are, and what are the cases when a program would be O of 1, for example. And I put here an example where what we're doing is simply assigning a value to the count, but we don't have any for loops at all. And so in this case, the big O notation is saying that it's so fast that it's an O of 1, and you don't have to count from 0 to a maximum number called n, right? And that way, this is the fastest type of algorithm. And if we compare it with another one like big O of n squared, then what we'll see is we got a for loop here, and then inside it we got another for loop. Remember, for the O of n, we had several for loops for step 1, 2, and 3 combined together, but in that case we have for loop for step 1, and then we leave the for loop there, go to the next one, step 2, where we have another for loop, and then leave that one and go to step 3 where we got the last for loop. But in this case, if it's an n squared, then what we have is a for loop, and inside it there's another for loop. So what that means is if we are counting from 0 to 9, then each of the counts would have a for loop inside that we'd have to do too. And in this case, it's also counting from 0 to 9. So because of that, we have to do a lot more counting. And if we do the big O notation, we'll have to say that it's n squared in terms of runtime execution speed. Now, we have here another one where we got O of n log n, and we want to know what this means, right? And I have here an example where if the code is recursive, and it looks something like this, and we know that a recursive algorithm is supposed to call itself. So if the function name is compute, inside it there is a call to itself. And so because of that, it's supposed to run at a speed much faster than n squared. And in this case, it's supposed to be n log n. Now, the other thing here is that if it's continuously calling itself, when is it going to end? And that's why I put here dot dot dot, because in certain programs, depending on how you want to implement it, there would have to be a part there that would say that no, we gotta exit, we gotta stop the continuously calling ourselves. And maybe in this case, it could be that when the count has reached 9, then that's when we leave. Okay, and of course you can learn more about that if you refer to our Sanko, our reference, google.com. Maybe you can find sample code there as well. But the idea of a recursive code, I think, should be familiar with you, especially if you've taken any of those theory of algorithm classes that I think students should be able to take if they're learning computers and computer science. Now, if we look at the graph here, we want to compare log of n and log n, and we want to know which one will be um, the algorithm, for example, that would be much faster to execute or much slower. And it turns out, if we look at the graph here, we can see that the log n is going in this way, which means that it's gonna finish much faster than the n log n, because the n log n is going in this way. And if it reminds you of something exponential, then I think that you're on the right track. Now, we need to know which one's the fastest, which one's the slowest, and we need to do these comparisons, because if we're writing sample code or we're writing some kind of program, we have to be able to identify which one is the appropriate code to use for a certain task. And if we know that the big O notation is telling us this, that the runtime execution speed is n squared, then maybe we can look at an n log n runtime execution so that it's going to be much faster, right? If we look at the sample here from, in this case, is Stack Overflow. The other one was from Wolfram Alpha. If we have here the stackoverflow.com sample graph, we have a comparison between an n squared and an n log n and an n. We can find that the n is going in this way, so it seems to be pretty much just counting from 0 to n. But in this case, if it's n log n, it's going and moving upward in this way. which means that it's going to take more time to finish. And if it goes up in this way, which is really an exponential kind of curve, n squared, then it's going to take a lot more time to finish the code, the set of instructions. And because of that, uh, in this case, we know that the fastest would be O of 1, and then the next one would be the O of n, and then afterwards is O of n log n, and the last one would be O of n squared. And in this sorting, counting sort algorithm that we got for this question, the set of instructions after analysis is telling us that its runtime execution speed is going to be a big O of n.